Okay, so as I said, a confidence interval helps us kind of with half of our questioning. The significance test helps fill in the gaps where, like, all right, our value on the confidence interval, we're pretty sure it's between here and here, but is that meaningful to us? That's where the significance test comes into play. Yes, was there a hand here? No? Okay. We have 3 targets here. We're going to be looking at a lot of terminology today. I'm going to try to do my best to incorporate examples to illustrate what's going on. Admittedly, though, this is a little bit of like a technical procedure where there's some terminology that is just commonly used in statistical analysis, like these null and alternative hypotheses, p-value, those sorts of things that I want to introduce to you, but we'll be using example problems to kind of illustrate what's actually happening as we go through this process. And keep in mind, like, this is not like a one and done lesson. Next week, we're going to continue to practice this and do more with this on our own, okay? So we'll really kind of help drive home what's truly going on here. And the confidence interval and the hypothesis test introduction that we've had this week, this is essentially what we're doing the rest of the year. And that we are concentrating right now on a single population's mean. But these procedures that we are learning hold true for proportions. Okay? I did a couple examples yesterday with proportions, like this percent of the population agrees with this. And that's where you can get into some interesting questions when you analyze those sorts of things. We'll be looking at differences between means, differences in proportions, all sorts of stuff. Okay? So let's start with an example here, and this is definitely not me, but let's say I were to come in and start bragging about my free throw prowess, right? We've been using this example throughout our probability unit because they're independent events. And you don't see that all the time in sports. And this is an easily relatable scenario. So I'm going to claim that I make 75% of the free throws that I attempt. Okay, free throw percentage, 75%. Now, to test my claim, okay, you don't think it's true. Okay, you say, all right, here's a ball, here's a hoop, let's go and shoot 20 free throws right now. If you're truly able to shoot at a 75% clip, we'd expect you to make 15 of those 20. Now, there's some natural variation, right? That's no guarantee that 15 of 20 are going to be made. Maybe I make 16. Maybe I make 14. Okay? But I feel like I need to prove myself, so I go up there and I only make 8. 8 out of the 20. In other words, 40%. I expected 75%. I got 40%. Well, we just said that there's some degree of natural variation. Okay? I expect 15 out of 20. Maybe I get 14. Maybe I get 13. But if I'm really a 75% free throw shooter, would I ever only be able to put up 8? Okay, when I'm trying my best, and that's really like everything's even. Okay? Well, we can use probability to help answer that question. Okay? It's not so much just like yes or no, like this is actually what you're capable of, or no, you can't do it. Probability can help us answer how likely or unlikely something like this would be. So we said that this follows a binomial model. So what I did here is ran this analysis in GeoGebra. This is a binomial, 20 free throws with a 75% accuracy, the probability that I make 8, and I'm not just going to say 8, I'm going to say 8 or fewer. Look at this probability distribution right here. These probabilities are so very unlikely. The probability that I just make 8 of those 20 when I'm trying my best, 0.0008. But again, I threw in not just 8, but 8 and down, binomial CDF. So probability I make 8 or 7 or 6 or 5, all the way down through 0. Still only rounds up to about 0.0009. Okay, 0.09%. That's incredibly rare. For us to go into this with the expectation of 75%, and I only do 40%. For me to expect that and get that just as a fluke almost never happens. So, our conclusion here is probably going to be on the lines of, I'm rejecting that idea that I was a 75% free throw shooter in the first place. Because there's no evidence to support that. Now, this type of an analysis is what we're doing in statistics. There is an accepted belief, and somebody doesn't believe that it's true. So you can't just say, no, I don't believe it, disregard it. Okay? You could argue that that's kind of what's going on in society today. Okay? People are throwing around opinions without any evidence or support to back it up. Statistics is a tool to help you make decisions, and help you make logical and reasonable and scientific decisions. You'll see that this procedure we look at today falls in line with the scientific method. Okay? Statistics is the tool to help you with that. Now, the confidence interval, okay, that is one of our common types of statistical inference. The other is these tests of significance. Okay, the confidence interval, you use that when your goal is to estimate a population parameter. Okay? You're trying to find a value with a confidence interval. A test of significance essentially boils down to a yes or no answer. Okay? What you saw as your data, is it showing you what's actually happening? Is it truthful? Is it honest? So that you can reject any preconceived notions? Or is it not strong enough to say that? It's essentially a yes or no answer. Okay? It has a different goal: to assess the evidence provided by data about some claim concerning a population. Okay? So this test that we're doing is a formal procedure for comparing observed data with a claim, also called a hypothesis, we'll get into that, whose truth we want to assess. Now, significance tests use an elaborate vocabulary, but the basic idea is simple. An outcome that would rarely happen if a claim were true is good evidence that the claim is not true. Flash back to, for some of you, this same classroom 3 years ago, and I taught you as a freshman. We're looking at geometry. We said in our proof unit that you've probably tried to erase from your memory by now, to show that something is not true, all you need to do is provide a single counterexample. That's essentially what's happening here with significance testing, is that you come into this process with an accepted truth, and you're trying to show that it's not true, that you have evidence, you have data to illustrate that it's not true. You're trying to throw a counterexample into the mix here. And it's not just like a single thing, but it's the abundance of evidence that you've spent all of this time and effort and money collecting. this unit here and the rest of the year is like the culmination of everything that we've done up to this point. Okay? Data collection, data analysis, probability. They're all tools in our tool belt that you'll see throughout our process today. So let's have an example problem as kind of our guide through this process. Artificial sweeteners that they have in like diet soft drinks, diet colas, things like that. The way they are chemically created, they gradually lose their sweetness over time. Yeah? Now, manufacturers are trying to improve their recipes and improve the chemical balance of these sweeteners. And they're trying to determine the effectiveness of that process. And people's tastes vary. Okay? So they're using a sample and they're measuring this on a scale. Now this scale goes -10 to +10. And because the purpose of this scale is to measure sweetness loss, a positive score corresponds with a loss of sweetness. Conversely, a negative score would correspond with a gain in sweetness. Maybe some people detect a gain or an increase in the sweetness. Okay? That's indicated by a negative score. So, a score of 0 would mean no change, no difference in the change of the sweetness. Now, suppose we know that for any cola, this sweetness loss scores, they vary, we said, taster by taster. People's tastes vary. But they follow a normal distribution, and the standard deviation of that distribution is 1. The mean, mu, for all of these tasters measures a loss of sweetness and is different for different colas. Okay? So here are the sweetness losses for the cola currently on the market as measured by 10 trained testers. Okay? So admittedly, that 10 is a pretty small sample size. But let's go with it here for our initial analysis. We can see that most of these scores are positive, which means that most of these participants detect a loss in sweetness. There are a couple people, though, -0.4, -1.3, who actually detected an increase in sweetness. But you average all of these together, and that sample's mean is about 1.02. Okay, so on average, they detect an average sweetness loss with a score of 1.02. Now, the losses are small. And we did say that 2 of these people detected a gain of sweetness. Does this data suggest strong enough evidence that the cola lost sweetness in the storage process? Okay? I mean, look at some of these scores. Okay? 0.4, 0.7. Okay? Our most extreme value on a scale of -10 to +10 is 2.3. Okay? Maybe it's not any significant change, and it could just be a fluke. Okay? Go back to my free throws. I expected 75%. If I got 70% in my sample of 20 free throw attempts, yeah, maybe I was having an off day. Okay? Same kind of thing here. We need significant enough evidence to be able to reject this pre-held notion. Now, we make a claim and we ask if the data give evidence against it. Okay? So because we seek evidence that there is in fact a sweetness loss, we are testing the claim that there is not a loss. Okay? We need to know what we're going into this with. Okay? So in this case, the mean loss for the population of all trained testers would be 0. We're going into this with the expectation that there's no change, there's no difference. There's no loss in sweetness, but there's no gain. That everybody's opinions about it should average out to 0. So if that claim of 0 is true, this sampling distribution with our sample mean x bar follows this normal curve. Okay? So again, it comes down to this visualization that we expect our 0 right there in the middle. And because it follows the rules of a sampling distribution, we set our population standard deviation, which there's a little typo here, that's not a 2, that's a 1. Okay, on the previous slide. Sigma over square root of n. Okay, again, this is our standard error calculation. Okay, this is our standard deviation step size on our sampling distribution. So 1 divided by the square root of our admittedly small sample size of 10 gives us a step size of 0.316. So, carry this out here, 1, 0.3, I'm just loosely rounding here, 0.3, 0.6, 0.9, carry that out there. Our sample's mean was 1.02, which would be out here somewhere. What's the probability that we expect this and we get this? Well, we can find that probability. We can go to our z-score chart, or we can use our technology to help answer that question. We saw that with the binomial model on the free throw example. This fits this normal distribution. Okay? We're not just going to say, like, yeah, we expected 0, we got 1.02. Yep, throw the baby out with the bathwater, throw out everything that we held about sweetness lost in artificial sweeteners. Okay? No, well, this was across a sample of 10 people. We want to know how probable something like this is. A good way to kind of compare this, and this is a metaphor that we're going to use kind of through the rest of the year, is to look at our judicial system. Okay, I said that we go into this statistical process with the idea that what we previously know to be true is true. Okay, it's the status quo. Okay? And we're going out on a limb to say that we have evidence that we're going to reject the status quo and that something else is actually true. This is actually what's going on. It's kind of like our judicial system in that we take pride in ourselves that in this country we have the presumption of innocence. You are innocent until proven guilty. So, we're going to be talking about these hypotheses. Okay? Our initial assumption, our null hypothesis, when somebody is accused of a crime, is that the defendant is innocent. And it's the job of the prosecutor, it's the job of the state to collect the data, collect the evidence, and present it to the judge and the jury so that the jury considers all the evidence and determines that there's no way that I could see all of this evidence happening with that presumption of innocence remaining true. And the jury has to make a decision that they are either going to reject that presumption of innocence and say that the defendant is guilty, or they're going to say that we've seen all this evidence, it is not strong enough to be overwhelming to say that, no, this person is not innocent, that they are guilty. So they come back and say, no, we find the defendant not guilty. Okay? We cannot reject that null hypothesis of innocence. Okay? But we're going to use that metaphor moving forward for the next couple weeks. because that really helps it sink in. Okay, we don't want to go out on a limb and just start rejecting all of these preconceived notions. Okay? We don't want to immediately throw everyone in jail who's accused of a crime. We only want to do that if the evidence is overwhelming and basically it's proof that the person did the crime. Okay? So we'll revisit that in the coming weeks. So this terminology, I had said that this assumption about what's currently going on, what's currently true, is called the null hypothesis. And the null hypothesis is represented by this symbol, H sub O. Now, the null hypothesis, it's like the status quo. And in our case, we're saying that there's no difference between what we see and what we're comparing it to. Okay? It's designed to assess the strength of the evidence in this test against this null hypothesis. Now, what we believe is going on is our alternative hypothesis. Okay? It's the claim about the population that we're trying to find evidence for. This is notated by H sub A. Sometimes you'll see it as H sub 1. Okay? But this is the more common way of writing it. H with a subscript of A. Now, this alternative hypothesis, it's either one-sided or two-sided. And I'll explain what that is, but we're going to have to look at some examples to see exactly what that means. The alternative is one-sided if it states that a parameter is larger or smaller than that null hypothesis value. If you're just saying that that alternative value is different, then it's a two-sided hypothesis. So let's visualize it like this. Our null hypothesis is always going to be equality, okay? Or some form of equality. We have it as just an equal sign here. But technically it could be greater than or equal to or less than or equal to. And I don't really want to get into that right now. In our sweetness example, our null hypothesis is that the mean is 0. That there's no change in the sweetness of these artificial sweeteners. Okay, that everybody's interpretation of the sweetness averages out to 0. But we think that the sweetener diminishes over time. So that sweetness score is actually going to be positive. So our alternative hypothesis is that this average should actually be a number bigger than 0. This is a one-sided alternative hypothesis. Okay? Now, if we had said that the artificial sweetener actually increases in sweetness, then it would be that our average score is going to be a negative number and it would be a less than symbol. But that's still a one-sided alternative hypothesis. A two-sided alternative hypothesis uses a not equal symbol. And in this example, that would have meant that, well, it's kind of erratic. We don't know if it's going to lose sweetness or if it's going to increase in sweetness, but the sweetener changes over time. Okay? There's a difference between no change and change in either direction. That would have been a two-sided alternative hypothesis. Okay? Now, at the moment, it doesn't really matter much, but in a couple steps, it will matter in terms of how likely or unlikely something is. Let me pause for a moment here. Any questions up to this point? Okay, we're looking at formulating our null hypotheses. H sub 0 H sub A, null and alternative. Let's look at another example problem here. It says, does the job satisfaction of assembly workers differ when their work is machine-paced rather than self-paced? Okay, here are the two things that we are comparing. A machine-paced assembly line or a self-paced assembly line. You're assigning workers to either an assembly line moving at this fixed pace or to a self-paced setting. All of the subjects work in both settings in a random order. So you can see, if you remember from our experimental design, this is a match pair design. Okay? They're trying both settings in a randomized order. Okay? After 2 weeks in each work setting, the workers take a test of job satisfaction. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. Okay? So self-paced minus machine-paced. Okay? Now the parameter of interest is the average differences in the scores. If there's really no difference between the preferences here, you would expect this to be 0, right? Somebody has a score of 10, somebody has a score of 10, because they like the same for both. 10 minus 10 is 0. There's no difference between the two. But the authors of this study want to know if the two work conditions have different levels of job satisfaction. That's a key word there. You're going to have to read these problems carefully to decipher if the alternative hypothesis is one-sided or two-sided. That word different indicates a two-sided alternative hypothesis. We have no idea going into this if people are going to prefer the self-paced method or the machine-paced method. Unlike the sweetener example, where we thought that it was losing sweetness over time, so we went into it with a one-sided alternative hypothesis. And this takes a little bit of practice to get a feel for what constitutes one-sided or two-sided. And we'll be doing that, so don't worry. But this one, we don't know if that average is going to be bigger than 0 or less than 0. Okay? This is a two-sided alternative. Now, if we go through this process and we find that there's a little bit of a difference here. Okay? We expected this, we got this. How much of a difference is meaningful to us? Because there is some accepted natural variation there. I always go back to the example of the coin flips. And you flip a coin 100 times, you expect 50 heads, 50 tails. But if you get 55-45, that happens. If you get 90-10, that doesn't happen. So where is that borderline between what's acceptable variation versus what is unexpected? That's what this process hopes to answer. The null hypothesis states that the claim we are seeking evidence against. The probability that measures the strength of the evidence against the null hypothesis is called a p-value. P-value is a probability. It is the number that helps us assess likelihood. Okay. Now, the test statistic calculated from this sample data measures how far the data diverge from what we would expect if that null hypothesis is true. Large values of this test statistic show that the data are not consistent with the null hypothesis, H sub O. Okay. This term test statistic. Okay. For right now, we are using a z-test. It's based off of z-scores in our normal distribution. But we're going to be doing other tests based off of the conditions for our data. Okay. I tried to emphasize a few days ago that in order to use these equations, use these rules, use these tests, we need to satisfy these conditions. We'll be looking at other tests, a t-test, chi-square test, ANOVA tests. All of these tests have their own test statistics, but they all come down to a p-value, because the p-value is the probability. And the probability that's computed off the basis that that null hypothesis is true, that statistic would take a value as extreme or more extreme than the one actually observed. That is what that p-value represents. The smaller the p-value, the stronger the evidence of H0 against the null hypothesis provided by the data. Here is our key sentence. The smaller the p-value, the stronger the evidence against H0 provided by the data. The other way we could remember this is with a questionably school-appropriate phrase that I guarantee you're going to remember for the rest of this year, throughout your statistical work in college and beyond. If P is low, reject the H0, the null hypothesis. If P is low, reject the null hypothesis. Right? You're looking for a small H0, or I'm sorry, a small p-value to reject that null hypothesis, a small probability, meaning that I'm expecting this. Okay? I expected to shoot 75% of my free throws. But when it came time to put up or shut up, I only did 40%. For me to expect 75 and get 40%, okay, you saw my probability on GeoGebra there. It was 0.0009. That's a low p-value. P is low. Reject that null hypothesis. I'm not a 75% free throw shooter. Okay? I'm worse than that. I'm lower than that. It's different. Okay? I'm not saying that I'm as bad as a 40% free throw shooter. Maybe I was having an off day, but the evidence I provided was not good enough to support my 75% claim. Okay? If that p-value is not low, then we don't have strong enough evidence to reject that null hypothesis. Okay? So we just go with the null hypothesis as being true still. So, small p-values are evidence against the null because they say that the observed result is unlikely to occur when the null is true. Large p-values fail to give convincing evidence against the null because they say the observed result could have occurred by chance even if the null is true. So the question starts to become, right? P is low, reject H0. How low is low enough? Well, you might not be surprised to learn that there is no definitive answer. It can vary as to how small you want it to be, but typically we write this as an alpha level. Okay? There's a typical level of acceptance. Anything less than 5% is small enough. But that's not written in stone. That can change. I said yesterday that with our confidence intervals, we use a 95% level of confidence most of the time. It's not a coincidence that we use a 95% level of confidence and alpha is 0.05, the remaining 5%. Okay? There's that 1-2 punch I was talking about. You're 95% sure it's between here and here. We're looking for our p-value to be less than 5%. It all comes back to the normal curve. Okay? If this is where our confidence interval says we fall, our p-value we're looking to be out here in the remaining 5%, in the tails. Okay? With some medical tests, we need to be very precise. We need to be certain before we start prescribing some new drug or before we start doing this new treatment. Okay? So they might be looking for a p-value that is less than an alpha level of 0.01 or 0.001. Okay? And a confidence interval that goes with that. Okay? It's unlikely that you're going to see an alpha level bigger than this, though. Like if you were to see an alpha level of like 0.10 or 10%, you're saying that you're okay with 10% of the time, or 1 in 10, expecting this and getting this, just as a fluke, just as natural variation? Yeah, it happens. You're kind of saying like, well, yeah, this weird coin that I flip, okay, yeah, you expect 50 heads, 50 tails, but every so often, 1 out of 10 times, you'll get 90 heads and then 10 tails. It just happens. We just deal with it. Okay? You want something to be less naturally variable than that. Yeah? But this whole process is determining. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. The quantity alpha is called the significance level or level of significance, depending on how fancy you want to be. So, essentially, we've done this process here. And I mentioned that this goes hand in hand with the scientific method. Okay? First step is determining the null and alternative hypotheses. H sub O, H sub A. And then you start to collect your data and summarize that with a single number called the test statistic. Okay, we haven't really gone into this just yet. We will in just a moment. Okay. I love how this is just kind of thrown in here. It's like, oh, step 1, okay, make the null, make the alternative. Step 2, collect the data and move on. Like, this is a big process right here. All of like our first line of step 2 was like everything we've done in the first semester, right? Collecting data, make sure that your sample is representative of the population. Make sure that you are getting to everybody and big enough sample size. Like there's a lot of work and effort that goes into that data collection in an authentic, accurate manner. Okay, so don't just brush it off as like step 1, step 2, step 3, step 4. Okay, most of the grunt work is on step 2. Step 3, determine how unlikely it would be to get that test statistic if that null hypothesis is true. This is what's accepted as the status quo. It's accepted as the norm, but you feel you have evidence to throw it out and reject it. And then lastly, make a decision. Okay? At the end of this process, you're deciding, I feel that either the null hypothesis is true or the alternative hypothesis is true. What does that mean in a more practical sense? Okay? Back away from this. We're not going to leave it as reject the null or fail to reject the null hypothesis. What does that mean in the context of my scenario? So specifically for our single population mean, we're going to start by looking at a z-test. So the way this works, you're taking a simple random sample of some set size n from a normal population that has an unknown mean and I'm going to put quotes around this, a known standard deviation, because we said that you don't know the population's standard deviation. Okay? When you're admitting that you don't know the population's mean, okay, we're going to be substituting in the sample standard deviation, and we'll clear that up in the near future. Okay? But officially, we do know it. Okay? To test this null hypothesis, that it has a specified value, the null is saying that our mean is some number, some population mean. Okay? Right now, we'll represent it as mu sub 0. In our examples, we had seen that it was 0. Right? Our sweetness, it averaged out to 0. There was no change. Okay? Our other example, the machine paste or self-paced assembly. There was no difference in preferences, so it was 0. Okay? It's whatever predefined number. Now, that goes smack dab at the center of our normal distribution. We're taking samples. This is a sampling distribution. So we know that the step size for the standard deviation on a sampling distribution is found with our sigma over square root of n, our standard error measure. We've been using that for a couple weeks now. So this equation that we have right here is an updated variation of our z-score equation. Back in the first semester when we were looking at population distributions, a z-score was found by x, our value, minus the mean of that population divided by the standard deviation. That gave us a z-score, which related us in the population distribution to where we fit in with everybody else. Well, this is a sampling distribution, so that measure of standard deviation, the standard error, we now say is sigma over square root of n. Our value is actually our mean that we got from the sample. So x is really x bar, sample mean. This mu value is our null value. Okay? It's whatever this number was in the null hypothesis. Okay? So in this case, it was mu sub 0. Now, this process gives us a z-score. And again, a z-score is the number of standard deviations we are away from that center. This is where our one-sided versus two-sided alternative hypothesis comes back into play. Because let's say we go through this process and we get a z-score that places us right there. If it's a one-sided hypothesis, we're saying that we expected to be at the center. Our sample gave us a value out here. What's the probability that we are there or above? In other words, what's the probability that we have data in this tail? That's a one-sided alternative hypothesis. Or it could have been in the other direction. Okay? What if our sweetness was actually increasing? We expected 0. We got negative 1.02. What's the probability that it's there or lower in the negative direction? We would have a tail on this side. We can get these probabilities from our z-score chart or from the calculator or from GeoGebra. But if our alternative hypothesis is saying, I don't care if it's bigger or smaller, I just want to know if it's different. That's a two-sided alternative hypothesis, and we add both of these tails' probabilities together. And because the normal curve is a symmetric distribution, it doesn't matter if I am X number of standard deviations. No, I shouldn't use X. Let me use Z. Shouldn't matter if I am Z standard deviations to the right or Z standard deviations to the left. It's the same value. So I can just multiply the area in one of those tails by 2, and that gives me the probability, the p-value. This area under the curve, which is actually one of it is the decimals in those fields on your z-score chart. That is a p-value. two-sided alternative hypothesis, you multiply that data by 2. Questions so far? Again, I get that this process is kind of dry and theoretical. We've seen a couple examples. We're going to be seeing more examples over the coming days and as we practice with this. But I kind of wanted to set the table and get us in motion here. Here's one more example for us to wrap up with. This committee reports that the systolic blood pressure for males between the ages of 35 and 44 has a mean of 128 and a standard deviation of 15. The population's mean is 128, standard deviation is 15. Now, the medical director of this company, he has a sample of 72 executives, and he measures their systolic blood pressure, and it turns out that the average of all of their blood pressures is 126.07, different than the 128, and lower than the 128. Is his sample of 72 executives, is that evidence, proof that the company's executives have a different mean systolic blood pressure from the general population? Keyword, different. Is this indicating a one-sided or two-sided alternative hypothesis? Two-sided, yeah. We don't know if it's going to be smaller or bigger than that 128. Now you might be saying that 126 is clearly smaller than 128. So why not do this as a one-sided alternative hypothesis? Well, the reason is these steps. Our very first step is to state what the null and alternative hypotheses are, and then in order start collecting the data. So in this case, start measuring all of those blood pressures and then average them out. Going into this, you have no preconceived notion as to if the blood pressures of your sample is going to be higher or lower than the 128. It is actually unethical to start collecting your data, looking at the numbers and see, oh, look at this trend here. I think that I have evidence that it's actually going to be smaller than what the accepted belief is. Okay? I'm going to run this with a one-sided alternative hypothesis. No. That is an ethical violation. Okay, we talked about ethics a little bit. Okay? Now, it's not the same as like subjecting somebody to shock therapy or anything, but it's a violation of statistical ethics. Okay? Because you're manipulating the data, you're fudging the numbers, you're fudging the procedure. Okay? And it sacrifices the integrity of any results that you would get. Because it's easier to achieve statistical significance if it is a one-sided test, right? You don't have to multiply this data by 2 because you want a low p-value. If you're doing it as two-sided and you have to double it, it's harder to obtain statistical significance. Okay? But in this case, you don't know if it's bigger or smaller going into it. You just think it might be different. This is different from the sweetness example where going into it, they suspected that the sweetener was losing effectiveness. It was losing sweetness. So they went into it as a one-sided alternative. So, our null hypothesis that mu, the mean for the population, is 128. That's our accepted belief. The alternative is that mu is not equal to 128. And we want to know if our evidence of 126.07 is strong enough across a group of 72 randomly selected people to indicate that. So we go through our z-test to show that. And we'll do this by hand here, but next week I'll show you how to use the technology to shortcut this process. All right? We have our sample value, our sample mean of 126.07, minus our null value of 128, divided by our standard error measure, 15 divided by the square root of 72. We work this out, and we get a z-score of negative 1.09. So what that would look like is on our normal curve, we have our value right here, our mean, right there at the center. 1, 2, 3 standard deviations, 1, 2, 3 standard deviations to the left. We had a z-score of negative 1.09 because we were below the mean. We're below this mu value. So we were like right here. This is asking what's the probability that we will be there or lower, but it's a two-sided alternative, so we're actually 1.09 standard deviations above the mean as well. But we can just double whatever that decimal is that we get. We add all of that area under the curve together, and we get a p-value 0.2758. There is a 27.5% chance that we would expect 128 and get 126. 27.5%, that's more than 1 out of 4 times. That is not rare enough for just saying that that's natural variation, okay? Or that it's evidence that we have something going on that is more than natural variation. Okay? If we're comparing this to our alpha level of 0.05, it is not less than 0.05. Our conclusion is that we failed to reject the null hypothesis. Okay? We find the defendant not guilty. We don't have evidence that it differs significantly from that accepted null value. Any questions on that? It is important to recognize that we're not saying that the null hypothesis is 100% true. That 128 is the average systolic blood pressure for males age 35 to 49 or whatever that age group was. What you're saying is that in your sample of 72 people, it was not significant enough. But we know the bigger the sample size, the better. What if that wasn't 72 people, but 7,200 people? A difference of that much across 7,200 people might be strong enough. So you could rerun that test, and maybe you do get a p-value that is small enough. Okay? So all those things that we talked about, like with confidence intervals, and how they can be distorted based off of the different parameters, that holds true with the significance tests as well. All right, let's stop there for today. I recognize that that's a big process. Okay, we've been building up all year to this, and we're going to take more time to practice with it. But ideally, you're using the results of a significance test with the confidence interval results. There's that 1-2 punch. Okay, they're presented together. So I wanted to talk about them together. Okay. Next week, we're going to look at more examples. We're going to practice with this and clear up any confusion that you might have. You do have a homework assignment for tomorrow with confidence intervals, and I want to give you some time to work on that right now. All right? So, those of you in the classroom, if you want to borrow a book right here, please do that. Those of you at home, please work. If you have questions, I mean, we're here for another 15 minutes or so. Please ask. Okay?